Good day and welcome back. In this video we will continue our tour of triple integrals by investigating triple integrals in spherical coordinates. Similar to the previous section, we will begin by introducing spherical coordinates and looking at a few common surfaces. But let me recall for you the basics of cylindrical coordinates. The entire idea with the cylindrical coordinate system is to represent a point in three-dimensional coordinate system as a triplet r, theta, z, so that r and theta are the standard polar coordinates if you were to project that point into the xy plane, and then z just measures the height above the xy plane. And remember the standard formulas relating Cartesian and cylindrical. We have x is equal to r cosine theta, y is equal to r sine theta, and z is simply z. The Pythagorean theorem, or thinking back to polar coordinates, x squared plus y squared equals r squared. The typical assumptions, or maybe even let's think restrictions that we want to place on this, would be that r is strictly bigger than or equal to 0, and that the theta value is somewhere between 0 and 2 pi. But we can get around these restrictions if it's necessary or highly convenient for the example of interest. Typically working with negative theta values is something that we have done. Let's now begin our discussion of spherical coordinates. And from a big picture perspective, the idea is going to be the same. We want to take each and every point sitting in three-dimensional space and represent it as a triplet. In this case, our cylindrical coordinate system is going to be described by rho, theta, and phi. And let me describe each of these individually. The most intuitive aspect is rho. Rho is a positive quantity measuring the distance our point is away from the origin. So rho is going to be strictly bigger than or equal to 0. Theta, it turns out, is measuring the same thing it had previously measured. If we drop our point down to the xy plane, theta is that angle we get coming from the positive x-axis going in the counterclockwise direction. So the typical restriction that we would place is theta is between 0 and 2 pi. And lastly, phi is kind of mimicking how we've defined theta, but it's relative to the z-axis. So if we think about our point sitting in three-dimensional space, phi is going to be a measure of the angle coming down from that positive z-axis. And to make sure that each point is only represented in one way, we actually only want the phi to go from 0 down to pi. So in this case, the restriction on phi is 0 is less than or equal to phi is less than or equal to pi. We would also like a few equations relating Cartesian to spherical. And without going through too many details, let me draw in a triangle. We can think of this distance as being r, back to polar coordinates, and the distance above that xy plane as being z. And with this in mind, if we think purely in terms of cylindrical coordinates, we would have x is equal to r cosine theta, y is equal to r sine theta, and then we have z. And if we focus our attention on this right triangle that we have drawn in, we can rewrite both r and z in terms of rho and phi. So r would be rho sine of phi, and z would be equal to rho cosine of phi. So note the rho sine of phi is really representing our r, but we will think of these three equations as the relationships between Cartesian and spherical coordinates. And it's also worth noting that because rho measures the distance from the origin, x squared plus y squared plus z squared will be equal to rho squared. Let's now look at a few common surfaces that are easily described in terms of spherical coordinates. The first such example is to graph rho equals a constant. in spherical coordinates. And we're assuming that this is a positive constant to meet our above restrictions. Thinking about this in terms of a set of points, we're thinking of all points in spherical coordinates where the only restriction we have is that rho is a fixed constant. And recall what rho actually measures. It measures the distance we are away from the origin. So theta, phi, they can be anything, but rho is always this fixed constant c. So in words, this would be all points, c units from the origin. And I'd like you to think about this for just a quick moment. What surface would really represent all points some fixed distance away from the origin? And if you said a sphere, I agree. And we can also hopefully see this very quickly in terms of a few computations. If we start off with rho equals c, and we square both sides, we'd have rho squared is c squared, which would be x squared plus y squared plus z squared is equal to c squared. So it's precisely this equation of a sphere. So graphically, we have a sphere centered at the origin with radius of a constant c. And not surprisingly, I will note that spheres centered at the origin are going to be highly conducive to using spherical coordinates. So let's look at one more common surface. Let's graph the surface phi equals a fixed constant in cylindrical coordinates. And note our assumption is going to be that value of c is somewhere between 0 and pi. And if I wanted to think about representing this in terms of a set of points, we're thinking all points in spherical coordinates where rho and theta have no restrictions placed on them, but that theta coordinate is always c. And in order to help visualize this, let me just remind you what phi is measuring. Remember, phi is measuring an angle coming down from the positive z-axis. And if we know phi is always equal to c, but rho and theta can be anything, that means we could take this line segment and in a sense extend it indefinitely because rho can be anything, and then also rotate it around the z-axis because theta can be anything. And if we were to do that, what word would you use to describe this surface? And it is a cone. And we can very easily visualize this cone by simply taking the line segment we've drawn and rotating it around the z-axis. And let me note a few common examples. First, maybe some outliers in a sense. If phi was equal to 0, phi equal to 0 would correspond to this angle phi being 0, so we would have simply the positive z-axis. From a similar kind of argument, if phi is equal to pi, you would be on that negative z-axis. And one more kind of extreme case, if phi is equal to pi over 2, that angle of pi over 2 would put you precisely in that xy coordinate system. So this would indicate the xy plane. So these may not be the typical examples that we would think of as a cone, but the typical example we probably have been envisioning as a cone is this z equals the square root of x squared plus y squared, which we've previously encountered in cylindrical coordinates, and the equation was z equals r. Note in spherical coordinates, this standard cone would come down at an angle of pi over 4. So our standard cone would be phi equals pi over 4. And it's worth making this observation as this cone is something that does appear frequently in examples involving triple integrals. And let me note that I just realized that cylindrical above should be spherical. And to finish this introduction into spherical coordinates, let me note that spherical coordinates are well suited for describing both cones and spheres, similar to the previous two examples. So what's left for us to investigate is how can we set up triple integrals in spherical coordinates? And we will pick that up in the next video. So stay tuned and take care.